basically what I wanted to say is today we have this webinar in the Platform Zero project, and the topic is AI-driven process monitoring and control. So basically how AI enhances real-time process monitoring and decision-making in the thin film PV production. And this is within the Platform Zero project, which is a European Union co-funded project. This is the whole series that we are taking is basically a series of 5 different webinars where it started already last year, and there will be one exactly in 1 month, so on the 24th of April, where this is then what I show you today, basically already in demonstrator form, so which demonstrators we are using. So now some words to myself. I'm Lauren Ginner. I'm a scientist at the Austrian Institute of Technology, and within the Platform Zero project, I'm Work Package 3 leader, which is basically the development of AI systems. And I'm also scientifically coordinator of our subunit, which is AI-driven surface inspection. And my research areas are on machine vision and industrial inspection. And the technologies we're using, or I'm using, is mostly photometric stereo, light field, and 3D reconstruction. And yeah, basically also how such scientific instrumentations and systems can be integrated into running machines or running production lines. And of course, also a big topic is machine learning and AI-assisted machine vision applications. So a few words to the Austrian Institute of Technology. We are actually the biggest applied research center in Austria. We cover basically all applied science topics, so like in the energy sector, health, bioresources, digital safety, security, vision automation control, transport technologies, technology experience, and innovation system and policy. And I'm particular of the vision automation control. And as you can see, we are around 1,600 employees, um, basically covering mostly all the research topics in applied science of Austria. To our center, so the Center Vision Automation and Control also consists of 3 units. This is assistive autonomous system, complex dynamical system, and high performance vision systems. And I'm from this unit, high performance vision systems. Within this unit, we have different research fields. One is the high-speed sensing, so what you see here on the left side. So we developed even our own cameras. We have fast inline illumination systems and concepts how this can be basically also embedded on a system that runs as an edge device, and where all this high-speed concept in form of direct data processing on an FPGA can be performed. A second branch is this inline computational imaging. Here we developed algorithms to simultaneously get 2D and 3D images, and basically support this all with algorithms in the background. And the third one, which is basically a topic of today, is AI-based inspection. So we combine vision and computation with AI and model-based data-driven models and learnings, and also semantic segmentations. So what is the context of the talk today? So as you may know, in 2025, the solar PV production reached a record of 30% of the European electricity production by generating around 370 gigawatt hours. And this is first quadrupling what we had in 2020. And secondly, also bypassing coal and hydropower. So it's really a major shift over the last years in the European energy mix. And this, if you're predicted for the future, it's expected to again double until 2030. So to reach 700 gigawatt hours, I think this is still a quite conservative estimation, but nevertheless, it's a huge number, which then is equally to 20% of the European electricity generation. And then with current policies, we will reach in 2040 above 2 terawatt hours, which would be then over 35% of the electricity in Europe. And you know that most of these modules are now silicon-based modules produced in China. But there is also a latest generation of PV technologies which combine both high performance and strong flexibility. And the big advantage is here that they can be produced so that you don't need like a silicon crystal that is grown, but you can produce them in a almost roll-to-roll manner, so basically in a continuous band. And exactly these topics are still quite strong in Europe in research, and are on the, I think, probably can be industrialized in the upcoming future, especially if you see the growth rates alone on the silicon that is predicted. And these systems can then be used for integrated PV in buildings, in vehicles, for agrivoltaics, or for IoT. And yeah, uh, however, the newest technology, so this thin film PV, has some disadvantages or some challenges that still needs to be addressed. And this is that the layer they are deposited need to be basically controlled very well to achieve really high performance. And as this is not yet on an industrial scale, this is still the area of research, and this is also where Platform Zero, our project, basically addresses exactly this upscaling and this how this production can be monitored. So this is the consortium. We consist of 12 European partners, with IREC being the coordinator, and us being the basically AI developers in the whole project. And we also have some producers like ZSW, Sunplugged, and Metzalo is a new partner, is also there. So now I want to give a bit of a background to machine learning in general, or to AI in general as a context, and then we'll basically step into the project itself. So why is machine vision an issue? Why is it so already broadly spread, and why is it even increasing in where it's all deployed? So first, it's very accurate and very precise. So you can detect down to 1 micrometer, basically everything, and with really high speed. Yeah, is very efficient, and it can be then used for improved process quality, and it's also very safe and stable. So basically, a camera that you put anywhere doesn't harm anyone, and therefore can also be used to reduce the costs in basically neglecting or reducing faulty production. However, classical machine vision deals with normal algorithms, which perform excellent if the data amount is still moderate. But as you all know, data amounts are vastly increasing. And therefore, if the data amount at a certain point reaches a level, it will be just really, really difficult in terms of performance that classical algorithms will compete with any learning-based approaches like AI or machine learning. So this gives basically also the legitimation for why AI machine learning is vastly used now in the whole machine vision context. So now to AI as general. So AI is basically a overall branch containing everything that is basically an algorithm to really a large language model and so on that mimics some kind of human intelligence. So this basically, let's say, the umbrella word. Then within artificial intelligence, there's the branch which is machine learning. This is a subset where the data amount is very, very, very big. Yeah, which where classical looking into the data is just failing because the amount is just too large. And then within machine learning, there is actually the deep learning, which is also a subset of machine learning and a subset of AI, which deals with neural networks and all the learning patterns. And this is I think the most famous one known now, with like all the chatbots, all the LLMs now run out there in this deep learning section. So a bit of maybe context and history. So how does this all work? So what is this neural network? So the first mathematical formulation of a neuron basically was already done in 1943 by McCulloch and Pitts, and they basically described a mathematical model how such a neuron behaves. Yeah, um, this was like the first basically mathematical formulation of a neuron, and this was done in 43. Then basically 10 years later, Frank Rosenblatt took that out and wanted to implement that as a perceptron, he called it, so like a neuron implemented on a computer in order to classify between. So actually, he wanted to use it already as a classification of an image, whether it can classify or basically get the knowledge of an image, whether it's a woman or a man in an image. And back then in 1957, the computers were very, very limited, so to say. So it just didn't work. Yeah. So he formulated that you have an input, you have some weights, and then some mathematical function, and then an output. And this is basically the how this mathematical formulation is being presented in a computer. Yeah. But unfortunately, it didn't work, and then basically the whole area of AI stopped developing for a couple of decades, actually. Yeah. And then in 1986, Geoffrey E. Hinton, which is mostly known for being the father of AI, he made a actually quite, yeah, maybe trivial, but also brilliant because nobody did it before. So he basically took up the implementation from Rosenblatt and said, okay, a neuron, as also in our brain, is not a single neuron; it's actually multiple layers of neuron interacting with each other. And then by learning something, the interactions between these neurons are getting stronger and stronger. So basically, by enforcing these connections, it's okay, kind of a feedback loop. This will basically fasten and really make the whole thing working. If you look at this mathematically, it's rather simple. So you have an activation function, then you have some weights, and this is basically then going to A1, A0, A1, A2. So this is the connections with different weights, and you can basically define a function, whereas the signal that is transferring is basically positive, so it's 1 or 0, defining by an activation function. So whether it's negative or positive, for example, then it's 1 or 0. Yeah. So it's actually rather simple. The trick is really connecting those into individual different layers, similar to what our brain does. So for example, our brain, we see an image there on the left side, so you see that as well now. Then it goes to the retina. In the retina, the system is basically, these are the first neurons transferred to another node in the brain, where it's transferred to another layer in the brain, to another layer in the brain, to another layer, and at some point there will be some logic behind interpreting or making us able to interpret it. This is a cat. Yeah. So the question is how these interconnections between those different neurons can be modeled and can be basically strengthened. And this is this was the $1 million question that Geoffrey Henstein also answered. So basically here a very simple example. You have an image of a bee and the image of a 9. Yeah. As an input. You have various different neuron layers, and you have in the beginning randomly distributed weights. Yeah. So basically, when it's the first run, it will randomly say this is a B or a 9. Yeah. So it will be, let's say, 50% of the answers will be wrong. Yeah. So 50% of the predictions are wrong, but we know the true values. Yeah. So we can generate the loss function from it. So telling basically the algorithm which is correct and which is incorrect. And this loss function is then used in a backpropagation to optimize these weights. Yeah. And if you run that a couple of times, a couple of billion times, because it's a computer, you can run it, retrain it as often as you want. At some point, it will generate the or almost always the correct answer. And this is basically similar to mimicking how we are learning this. Yeah, I mean, for us as babies, basically the parents will tell us this is a B, this is a 9. Yeah, and this is basically what is simulated here and as a mathematical formulation for the computer. And this is everything actually. So it's in the whole concept is rather simple, and you can input now everything on the left side if as long as you have some kind of feedback. And to optimize, basically have this backbook propagation, you can solve almost everything as our brain does as well. So it's very, very general, this concept. And there are also different types of learning. So one that we showed you now in this example is the so-called supervised learning, where we always know the answer, yeah, and basically tell the algorithm itself, that what is wrong and what is right. Then there's unsupervised learning. So basically here it's when there's a really, really large amount of data, and there's no label given. The algorithm will see, okay, how does it somehow cluster? What belongs to what is somehow linked to each other? And then there's the whole area of reinforcement learning. So here a classical example is a robot that tries to do something. If it's not done as it should be, there is a feedback. So it's basically always trying and retrying. So this is what is always used also in this whole area of humanoid robotics, where the robot basically tries often and often in simulations how to the actuators should be moving to have almost human movements. So there's also no like a better learning method or a worse learning method. They're also, you can use all of them. Yeah, it always depends on the problem that you're facing. So how then to choose which kind of networks are we choosing, which kind of learning methods? So this basically is all determined on what problem you want to solve. As a rule of thumb, you can say, okay, if you want to have a classification or regression tasks, fully connected networks are probably the most efficient way to go. If you have visual or spatial data, then convolutional neural networks are a very good choice. Or if you have like time series or text recognition, then some kind of feedback is necessary. So recurrent networks or transformers are probably the best choice. And transformers are the ones which are now used in all the large language models and forms of transformers, of course. Okay, so now how does this relate to our project? So within Platform Zero, we have various processes taking place for in the PV production. So we have advanced sensor stations here, depicted now as Advanced Sensor Station 1, Advanced Sensor Station 2, and so on. And they each look at the after a process that is happening, so some physical process, some deposition of some layer or whatever. After that, the sensor basically looks onto the product and collects data. Yeah? And then we have an AI system which basically structures all this data. So they are all structured in a database. And then based on all these inputs, wants to predict outcomes. So it basically monitors what is incoming on data and also relates it to physical processes. And this can be then used, of course, for first prediction. So prediction in terms of, is the process okay? Is it stable? Yeah, and also then to use as a monitoring. So if something goes off, yeah, some sensor inputs basically drop because something is incorrect in the process, it can be used already for process control directly. So now for our Platform Zero project, we have these samples. Yeah, these samples present basically here individual steps, individual processing steps. Yeah. And we have them from ZSV, we have from Luridera, we have from Samplect, and from Solid Technologies, various different samples. First, always in the first step where we had 10%, so we had basically a standard production, and then the producers forcefully changed the production environment to have a 10% plus minus deviation of the process in the first set, and then plus minus 2% deviation for the second set. And then, of course, we also had additional samples in order to that each producer and each sensor producer could also focus their sensor and design their sensors to achieve basically results that are somehow classifying for those changes. So here's such an example. So we had, for example, Raman spectrum, we have photoluminescence, we have reflection percentage, we have near infrared and visible inspection. And we imaged those samples and saw whether we could differentiate them in the sensoric inputs. We also have a vision system, which we use from the EIT developed, and a reflectance percentage image, which is used where we also saw quite nicely how we can differentiate between different standard and deviation. Then we have IV measurements, we have lips and PL imaging and so on. So there's a vast amount of sensors. They all aim to characterize what's going on in each individual process. So how is then this terms? So this AI system, how is then this whole architecture and concept working? Yeah. So we have this production process. We have these advanced sensor stations. In these sensor stations, the sensors collect basically raw data. Yeah, and these raw data come from multiple different providers. So as I said, all the sensor producers, so IREC, AIT, HZB, and UPO, they basically handle their own sensor, yeah, and only manage the data upstreaming. Yeah. There's one central PC, which is basically the master, and it aggregates all this data and uploads it to a database, yeah, which is provided by RISC, so one another partner. And then, as the advanced sensor station is rather decoupled from processing, we basically it only focuses on which hardware is needed to, so which sensors are needed, how the synchronization can be done, and how the data collection is working. So there's no need for any local processing, which should minimize the complexity and also make it nicely scalable. So if there's a new sensor, you can just add or remove them by having as a single module, basically, that can be added or removed. Then on the cloud, so all the raw data is basically stored. In the cloud, there, depending on the sensors, there can be some KPI extraction happening. So this is dependent on each sensor producer. So for example, for visual, we have some kind of machine vision algorithms running where like cracks are detected, dots are detected, and mean colors are detected. And these can all run on so-called Docker containers to basically extract from this raw data direct process data and stores it also in a results table. This has the big advantage that, yeah, it reduces the CPU requirements for the sensor station itself. Yeah, it enables parallel processing. So of course, many of these Dockers can run in parallel, and it also ensures that the processing and basically prediction is decoupled from the acquisition, which makes it also more stable. And then for the decision making, so basically this all these KPIs are then fused together, and then on the cloud there can be machine learning models that be applied, which uses these extracted KPIs or the raw sensor data, basically everything that is available, and then based on what is there, makes a prediction. So this is the overall concept, basically. And the big advantage is with this concept, we are quite flexible. So we can add, remove sensors depending on which process is happening, which at which location the sensors are employed. This basically reduces the requirements also in terms of hardware. So basically, we generate this platform, this overall concept where you can add or remove models, modules for sensors. So how does this look like as an example? So here we have, for example, process one, we have some process parameters, and we have some sensor parameters, and then we have the raw data coming out. So for example, here we have sample ID, let's say this is the sample one, yeah. Then we have the advanced sensor station one in this case and sensor one, and we have some sensor parameters like acquisition speed, illumination intensity, temperature, whatever can be inserted there. And then the raw data, like for example in the vision system, the images, or in the Raman system, it can be the spectrum, the PL, again a spectrum. So depending on whatever your sensor is basically outputting. And like this, we can deal with many different sensors, yeah, and many different configurations and many different modules. Yeah. And as you can see, all these inputs basically look quite different. Yeah. But as we anyway store them all on the file storage, have then the KPI extraction running, and then this can be fused to a so-called results table where basically the extracted KPIs are then fused together. And this is then, of course, stored again in the file storage or in the database, basically. And now having this, we have, as shown before, we have these Docker containers, which produces this fused results table where all the data fusion is happening. And in the first stage, we also know the label because now the system still needs to basically train. So we need still some models to be trained. So in the first stage, we know the label, so we know that it's standard deviation plus or deviation minus. Yeah? And these labels with this fused data can then be used in basically a decision-making AI in order to predict the labels, whether it's a good or a faulty production. And this was done on the 10%, so the batch 1 data and also the batch 2 data. And here I will show you again just an overview. So basically we have this process, we have this sensor concept, how the data is stored on the database, how on the database the results or KPIs can be extracted, and how those can be then used for decisions. So now here we did an LDA analysis of the batch 1 data. So keep in mind that we had here plus minus 10% deviation. So we did first experiments and basically used 80% of the data that was available for training, and then with the model 20% for testing, and it showed very good classification. So you see that basically we achieved 100% of accuracy in terms of dividing between standard deviation minus deviation plus. But we had quite a limited amount of data. So the statistical significance of this data was a bit weak. We used an LDA on visual information, XRF, Raman, and so on. So on all this data which was available. And yeah, as I said before, we only had 45 samples. And this, we also did a bootstrapping analysis, which showed basically that our confidence interval, so having 100% is of course excellent, but this makes us always a bit suspicious as it's so good. But I mean, 10% is also a big change. But if you look at the 95% confidence interval, you see that it stretches from 0.77 to 100%. So this indicates a very high uncertainty. So the system or the model will probably be over optimistic, and the performance might be worse than it seems like on this. Yeah, may not generalize well. So basically, our finding was that we definitely need way more data. As for every machine learning process, you always need a lot of data, a lot of labels, a lot of information that can be fed. And we got this additional data basically on 11 additional samples. But these were actually not foreseen in the project. But as the production of the batch 2 samples took a bit longer than anticipated, we used these artificial samples. So they were from casterite. So it's another method of thin film PV. And they were actually clustered in 14 by 14 individual PV cells, each with slightly different process parameters. And they were also divided into standard and non-standard. So basically deviation plus, deviation minus, and standard. And there we had over 1,000 of these cells, so the sample number was quite significant. And we used the same LDA, used also 80% for training, 20% for testing, and showed that even with a split of 50 to 50, we could go down to got an accuracy of 99.8%, so very, very excellent, and showed us that LDA as being a really trivial machine learning classifier still worked pretty nicely, and is a good starting point because it's you highly understand what's going on in this in an LDA. Yeah. So now for the patch 2 samples, so we had here 3 different processing steps. So we had the first one, this 6 absorber, and we got, so this is how they look like and how they're fused basically, and all these sensor stations are fused together. Then we have the second process where the CDS buffer is basically applied. And then we have a third process where the TCO deposition is made. Yeah. So we had all these 3 different processes, and each now with a plus minus of 2% of deviation. So this is now much closer to an actual production scenario. And here we did the same. So we used LDA as a first classifier. We have 324 samples, so this is now a significantly larger number. We have still used 80% for training and 20% for testing. And you can see here basically the LDA map and also the confusion matrix. Basically what you can see is that only one is misclassified. And this brings us now to a nice thing that we can do, as we have all these data synchronized and with all the same sample. So we have now all these different sensors, so PL imaging, PL, PS, MPL, R-INGAS, Raman, and so on. And you can, of course, use all of them in this fused manner, as I showed before, or you can also use them individually, and run each sensor individually and see how well they classify. As you can see, some are actually very weak in classification accuracy, some are better, and some are really excellent. Yeah? And overall, we end up at 96.9 percent of accuracy and F1 score. You see already here a large spread within the sensors, so maybe a different approach than LDA might be suitable, but nevertheless, we used it now for the first evaluation. And still, there's 324 samples are still in the language of machine learning, not a lot. Yeah. To get a bit more of statistical significance, we basically did 100 runs of random splits of this 80-20% testing and training, and show here basically the minimum of all that could be achieved and the maximum that could be achieved. So the maximum reaches also already 100%. And the mean over all these 100 runs was 96.2, which is already a very excellent results, considering that we um, that we basically use just as the LDA as a classifier. Yeah. We use the same concept now for the second stage, so for the CDS buffer deposition, and here had actually in this showcase 100% of accuracy, which is also nicely shown here in these individual sensors. You can see here that we used already different sensors here. So for example, MPL was not used here as an example. And here actually all of them show really good performance, but still you can see some better, some worse. And again, if you run that 100 times, we end up with a mean accuracy of 99.77%. So this is really, really excellent performance. And now for the last stage, for the TCO deposition, similar graph, similar numbers, similar statistical robustness, let's say. So this gives us very, very confidence feeling that the overall concept that we're using works really well. And we also, of course, also tried it with some plugged samples. Here you see that the overall classification is a bit weaker compared to the ZSW, which may be due to different processing steps or handling of the probes. This is something we don't know yet, but nevertheless, you see that individual sensors like PS, for example, shows really, really excellent accuracy here. Yeah. So here, especially this case, gives us an insight because here we have 99.3% of accuracy, and overall we only have 89.7%. So maybe a different classifier would probably be more suitable for this particular processing step. The same is true for Sole, ETL printing and drying, where we have also in individual, so in PS, a really high accuracy, and in reflection and transmission, a really low one. So overall, that brings us to the conclusion for the LEA classification. So we had this 100 runs with the 80-20 splits, and we end up in the ZSW case with always above 96%. In the sampler case, a bit weaker, between 83 and 87% of accuracy, and in the Sole reaching from 78 to 86%. So here's basically the weakest performance. And what is also interesting that we, as I said already, can now go into each sensor individually. So this is basically shows just graphically which this means for each sensor that we can see here. And we can start actually physically modeling what is happening. So this is just a graphical representation of one such of fused sensor inputs that are used. So this is PL, PS, reflectance from CCD, reflectance from INGAS, and Raman spectrum all fused together in one results array. So this is just that we have something to visualize. And you can see now in the LDA where the dot peak of the covariance matrix is, then also what is the top contributing feature for each sensor individually. So for example, for PL, it's 1191 arbitrary numbers now. Yeah, so you would not now need to look into what this means in your sensors. For PS, it's albedo mean e.g. green, as you assume, yeah. RCCD is 509, and so on. So basically, it gives us already insight in the sensors where and which particular feature is responsible for the classification. And you can also, over the all the sensor fused sensors, you can of course just take the 5 top contributing features, and you can see that in this case they're all from the photometric stereo system, um, having this albedo mean and so on. So this knowledge can then be used actually for a really detailed analysis of what's going on. Yeah, and here now already a prediction of other classifiers than LDA. So as said before, LDA is very good as a first testing classifier, also because it's you can quite nicely understand it. You don't know, there's not so much hidden behind it, and um, yeah, it works really well um, as a classifier. But on the PS case, you see it's really high numbers, and overall it drops. So we tried different classifiers for here, for example, the light gradient boosting machine classifier. And here, basically, it maintains the highest classification accuracy. So having all these together, you still have the same overall performance. So this might be a good choice for this particular processing step and can be envisioned like this. So we basically born the idea that we will test different classifiers that are available to evaluate their performance. So we actually found 26 different classifiers, and we had now all these data from all these different processing steps. We separated them in different testing and training ratios, so reaching from 80 down to 20. Yeah? And we did that in 3 randomized runs and combined all these results, basically fused them together. And then we calculated a score, basically, which is weighting the accuracy a bit stronger, the balanced accuracy, and the F1 score. And you can see overall the LDA that was used initially had actually a quite good performance of 92%, but there are better ones. For example, this light gradient booster machine, where we reach 97%. Yeah? So basically, the data and the concept as we show it now proves really good separability and classification accuracy. And now you can actually start to visualize. So how can this be implemented in a potential workflow then on the machine floor? So we have, for example, processing steps 1. So we have this all diffused data from the sensor 1. You have the performance, and now here, for example, LDA still for each sensor individually. You can now look, okay, which machine learning classifier is the best for this particular processing step. So basically, in the learning phase, you can still think of what is happening in this process, which sensors are really good, and which classifier works the best. Then you choose it. Then you go into physical modeling. So you look on the actually fused sensor. You think about, what does this mean physically? So what's actually happening in the process? So there, of course, like experts from the domain can contribute their knowledge on that size. And then this can basically be fused together. So the physical modeling and which classifier works the best in order to help, for example, here, machinist, which sensors to choose, which classifier to choose, and then you get a label. Now, in this case, very positive, of course. So, as a conclusion, we set up this whole AI architecture and defined it, and also how the whole logic behind should look like. We analyzed the batch 1 data, these additional samples, and the batch 2 data, and progressively evaluated to also refine our AI system. We showed that more sensor data improves first the separability, but also increases the diversity between different sensor inputs, and this may depend on different processing steps. Um, yeah, this is what I already said. And then basically the patch 1 data showed really good initial separability, but statistical robustness was a bit linking, but nicely the patch 2 samples confirmed our findings in the patch 1 with more realistic production environments, basically. And yeah, and the sensor contributions may vary by processing stage, offering really targeted insight into the physics, which is what is happening in the process. So what is then the outlook for the project, as the project is still ongoing? So we want to further establish a clear links between the sensor signal and the process parameters, which support a more targeted diagnosis of what's going on. We will finalize the GUI interface, so the graphical user interface for the operators, which should then include also predictions of the output and some confidence levels and some sensor parameters explanations. And we prepare a fully AI pipeline, basically all the where the data ingestion, the fusion, the prediction, and the explanation will be deployed in these advanced sensor stations. And this will be then configured and tested under real process conditions um, in order to ensure stable integration and reliable real-time performance. Okay, yeah, with that, actually, I already want to conclude my talk and want to thank you very much for your attention. I think overall for us, this was the last review meeting. Yeah, overall, at least from my side, the results are really interesting, and we will go on investigating how this will be then actually rolled out on the factory floor. And I'm really eager to see that being deployed directly in a machine or in a production environment. Okay, with that, thank you very much for your attention. And yes, I'm finished basically. So I'll hand back to you.
Thank you very much, Lauren. So, if anyone has any question, you can leave them in the chat. And I also wanted to let you know that all the webinars are available on our website, and this one will follow shortly. I just need to trim the beginning and the end. And so, yeah, if you have any question, now is the time. And if not, then we will release you shortly. So, thank you very much, Lauren, for the great presentation. And thank you everyone who attended the webinars. We will email you the replay shortly. And yeah, we will see you in the next one, hopefully.
Perfect. Thank you very much.